if the greatest alien civilization in the universe is not hiding behind a star, not buried under the ice of Europa, not floating in the clouds of Venus, not sending radio waves across the darkness, and not waiting for us somewhere beyond the Milky Way? What if alien life is already here, passing through us, vibrating beneath us, woven inside the quiet structure of matter itself? What if the most impossible form of life is not too far away for us to reach, but too small, too fast, too strange, and too deeply hidden for us to recognize? Before we look upward tonight, before we imagine spaceships crossing black oceans between stars, we have to ask a question that feels almost forbidden. What if life can exist at a scale where our eyes, our microscopes, our biology, and even our imagination begin to fail? We usually think of aliens as creatures with bodies. Maybe they have skin, shells, eyes, tentacles, bones, wings, or machines. Maybe they breathe strange gases, swim in methane seas, or crawl under orange skies. Even when we imagine something truly bizarre, we still imagine it as a thing made of atoms, something large enough to occupy space the way we do. But nature has never promised that life must be large. Nature has never promised that life must be soft, wet, carbon-based, or even biological in the familiar sense. Nature only follows rules, and if those rules allow stable patterns, energy flow, memory, self-organization, and evolution, then the question becomes unsettlingly open. Could life be a pattern rather than a body? Could life be a process rather than a creature? Could something alien exist not between the stars but inside the hidden music of particles? And as we begin this quiet journey into one of the strangest ideas science can allow us to imagine, stay with this thought. Maybe the universe is not empty between living worlds. Maybe it's full of forms of order we have never learned how to notice. So before we descend into atoms, fields, particles, and the shadowy border between physics and biology, take a slow breath, settle in, and if this kind of cosmic mystery pulls you deeper into the night, like the video, subscribe to the channel, and tell me in the comments what you believe life really is. Is life a cell? Is life DNA? Is life consciousness? Or is life something more ancient than biology, a secret behavior of matter itself? The strange part is that science does not actually have one perfect definition of life. We know life when we see a tree growing towards sunlight, a bacterium dividing in a drop of water, a whale singing through the deep ocean, or a human mind asking questions about the stars. But when we try to define it precisely, the edges blur. Life consumes energy, but fire consumes energy too. Life reproduces, but crystals can grow copies of their structures. Life adapts, but computer programs can adapt. Life maintains order against decay, but hurricanes are ordered systems fed by energy. Life stores information, but atoms store information in quantum states. Life evolves, but chemical systems can also change under selection-like pressure. So where does non-life end and life begin? On Earth, life is built from chemistry. It uses carbon, water, membranes, proteins, sugars, nucleic acids, minerals, ions, and sunlight or chemical gradients. It copies genetic information, makes mistakes, filters those mistakes through survival, and slowly changes across generations. This is the only life we have confirmed. Every living thing we know, from moss to microbes to humans, shares a deep family history. We are all built from the same molecular language. DNA and RNA store instructions. Proteins perform work. Cells form boundaries. Metabolism moves energy. Evolution sculpts complexity. That is real, beautiful, and scientifically grounded. But the danger is that we may confuse the only example we know with the only example possible. Astrobiology usually searches for life by looking for Earth-like clues. We search for liquid water because every known organism needs it. We search for carbon because carbon forms complex molecules. We search for oxygen, methane, carbon dioxide, phosphine, organic chemistry, energy sources, and atmospheric disequilibrium because these could hint at biology. We aim telescopes at exoplanets and ask whether their atmospheres look alive. We send robots to Mars and ask whether ancient water once carried microbes. We dream of drilling through the ice of Europa or Enceladus to sample hidden oceans. This is wise because real science begins with what we know. But this approach is also narrow because it assumes life leaves traces similar to ours. Now imagine another possibility. Imagine a form of life that does not produce oxygen, does not need water, does not build cells, does not leave fossils, does not send radio signals, does not make heat signatures that look biological, and does not interact strongly with ordinary matter in the way our instruments expect. It might not be alive in a human sense. It might not think, want, feel, or build. But it might organize information, it might persist, it might draw energy from its environment, it might replicate patterns, it might evolve. And if those patterns occur beneath the scale of atoms, or inside fields that pass through matter almost unnoticed, then even if it existed everywhere around us, we might never know. To understand why, we must descend, not just shrink, but surrender our intuition. At the scale of everyday life, objects have clear edges. A stone is here, not there. A hand touches a table. A planet orbits a star. But at the atomic and subatomic levels, reality becomes less like a collection of tiny solid balls and more like a restless field of probabilities, vibrations, exchanges and constraints. Electrons are not little planets orbiting nuclei like moons. They exist in quantum states, described by wave functions shaped by energy levels and probabilities. Protons and neutrons are not simple spheres. They are made of quarks bound by gluons, seething with virtual particle activity and strong force dynamics. Empty space is not truly empty. It contains quantum fields, and particles are excitations of those fields. Everything we call matter is made from this deeper layer. The chair, the wall, the blood in your body, the oxygen in your lungs, the dust between stars, the ice on comets, the iron in Earth's core, and the glowing plasma of the sun are all expressions of quantum fields. Atoms are stable because of quantum rules. Chemistry exists because electrons occupy energy levels. Solids feel solid because of electromagnetic repulsion and the Pauli exclusion principle. Light moves through glass because photons interact with matter in ways that change their effective speed through the medium. Radioactive decay, fusion, magnetism, color, photosynthesis, nerve signals, and the glow of stars all depend on subatomic behavior. We already live inside a universe where the tiny controls the large. So if life is a form of organized matter and energy, and if all matter and energy are rooted in quantum fields, then a haunting question appears. Must life wait until atoms assemble into molecules and molecules assemble into cells? Or could there be forms of organization below chemistry, perhaps not life as we know it, but something lifelike enough to deserve the word alien? This is not a claim that such beings exist. There is no confirmed evidence for subatomic organisms, particle civilizations, quantum microbes, or living dark matter. But asking whether physics leaves room for unfamiliar forms of complexity is not fantasy by itself. It is a disciplined imagination, as long as we keep one hand on evidence and the other on possibility. The first barrier is stability. Life needs patterns that last long enough to do something. A living cell is not permanent, but it persists for a meaningful time. DNA can store information, proteins can fold, membranes can separate inside from outside. Evolution needs inheritance. At the subatomic level, many particles are unstable. Free neutrons decay in about 15 minutes on average. Muons decay in microseconds. Many exotic particles vanish almost instantly. Virtual particles are not little objects living secret lives. They are mathematical features of quantum field interactions and cannot be treated like stable creatures. So any serious idea of subatomic life must face a brutal question. What structure could last long enough to store, transform, and pass on information? Some subatomic things are extremely stable. Electrons appear stable as far as we know. Protons are stable on unimaginably long timescales, at least longer than current experimental limits. Photons can travel across the universe for billions of years if they avoid interaction. Neutrinos can pass through entire planets almost undisturbed. Atomic nuclei can persist for ages. Quantum states inside atoms can store information briefly or in special conditions for longer periods. But stability alone is not life. A rock is stable, a proton is stable, a photon is persistent. Life requires dynamic order, not just endurance. It needs a way to process differences, a way to respond, a way to maintain itself while the universe tries to dissolve its structure into disorder. The second barrier is energy. Living things do not violate thermodynamics. They survive by feeding on gradients, sunlight against darkness, hot against cold, chemical imbalance against equilibrium, electron donors against electron acceptors. Earth's life is a river of energy flowing through matter. Plants catch photons and build sugars. Animals eat chemical order and release heat. Deep-sea microbes feed on chemical energy from hydrothermal vents. Even your thoughts are powered by electrochemical gradients across neural membranes. So a subatomic lifelike system would need some energy source. It might in principle draw from particle interactions, radiation fields, quantum transitions, plasma currents, magnetic reconnection, gravitational extremes, or unknown hidden sector forces. But again, possibility is not proof. The third barrier is information. This may be the deepest one. Life is not just matter arranged beautifully. A snowflake is beautiful, but it does not carry an evolving lineage of instructions. A flame is dynamic, but it does not inherit useful variations in the biological sense. Life stores information about how to continue being life. It copies itself imperfectly. It is shaped by selection. If subatomic life existed, its genetics could not be DNA unless it used chemistry. Its information might be encoded in quantum states, particle configurations, field oscillations, topological structures, spin networks, defects in fields, or repeating patterns in plasma. These are speculative, but they point toward a more abstract idea. Life may be information maintaining itself through energy flow. This is where the first great twist emerges. Perhaps the question is not whether tiny particles can become little animals. That is too crude. The deeper question is whether the universe permits self-preserving information patterns at scales smaller than atoms. On Earth, biology is a specific solution to the problem of information under thermodynamic pressure, but physics may allow many kinds of information systems. A virus sits at the edge of life because outside a host it is inert, but inside a cell it becomes part of a copying process. A prion is just a misfolded protein that can reshape other proteins. A computer virus is not biological, but it replicates and evolves in a digital environment. Life, once abstracted, becomes less about flesh and more about patterned persistence. But quantum information is strange. A classical bit is either 0 or 1. A quantum bit can exist in a superposition, a combination of states, until measured. Quantum systems can become entangled, meaning the state of one system is deeply connected to another, even across distance, though this cannot be used to send faster than light messages. Quantum information is fragile because interactions with the environment cause decoherence, turning delicate quantum possibilities into classical outcomes. In laboratories, scientists fight decoherence with extreme isolation, low temperatures, and careful engineering. So if there were lifelike quantum systems, they would face a problem biology rarely faces in the same way. The act of existing in a noisy universe could erase their internal organization. Yet nature can preserve quantum patterns in certain contexts. Atoms have stable energy levels. Superconductors show coherent quantum behavior across many particles at low temperatures. Some biological processes may involve quantum effects, such as tunneling in enzymes or energy transfer in photosynthetic complexes, though this does not mean consciousness is quantum magic. Quantum mechanics is already part of life because all chemistry is quantum, but life as we know it works mostly at the molecular scale, where quantum rules create stable chemistry without requiring whole organisms to remain in delicate superposition. A truly subatomic lifelike system would need a way to use quantum rules without being destroyed by them. Now think about detection. We do not detect life directly as life. We detect signatures. On Earth, we see cells under microscopes, chemical metabolism, genetic material, movement, reproduction, fossils, waste products, and ecological relationships. On other planets, we would search for atmospheric gases, minerals, organic molecules, seasonal changes, or maybe technological signals. But in particle physics, our detectors look for mass, charge, spin, momentum, decay products, scattering events, energy deposits, and interaction probabilities. A particle detector does not ask whether a signal has meaning. It asks whether a particle passed through, what it interacted with, and what came out. If a hidden system were alive in some alien sense, we might record its footsteps as noise. That idea should be handled carefully. Scientists are not ignoring obvious living patterns in particle experiments. Particle physics is extraordinarily precise. If unknown particles or forces interact with ordinary matter strongly enough, Experiments often constrain them, but meaning depends on the questions we ask. A radio receiver can detect electromagnetic waves, but if it is not tuned properly, a message becomes static. A DNA sequencer can read genetic code, but it would not interpret a poem carved into stone. A microscope can reveal bacteria, but not the economy of a city. Every instrument is a philosophy made of metal. It sees what it was built to see. The universe may contain patterns that pass through our categories without triggering the word life. The scale difference is almost impossible to imagine. A human cell is already enormous compared with atoms. A typical atom is about 1/10,000,000,000th of a meter across. A nucleus is roughly 100,000 times smaller than the atom itself. Quarks and electrons appear point-like at current experimental scales, with no known internal size. To us, subatomic events are tiny and fast, but to a hypothetical information system operating at that scale, the world above might seem frozen, vast, and incomprehensible. A human heartbeat might be a geological age. The movement of a hand might be like continental drift. A spoken sentence might stretch across epochs. We might be too slow to be noticed as living. This creates a mirror. When humans look at the cosmos, galaxies seem slow. Stars live for millions or billions of years. Galactic collisions unfold over hundreds of millions of years. We do not see a galaxy move in ordinary time. We infer its motion. Now imagine a subatomic system looking at us. Our lives might be like galaxies, slow storms of matter barely changing within its meaningful time. It might not recognize us as alive for the same reason we do not recognize mountains as creatures. Maybe scale hides life not by making it invisible, but by making its rhythm incompatible with ours. Time is not just a background. It shapes what can count as behavior. A mayfly lives for a day. A bristlecone pine can live for thousands of years. Bacteria can divide in minutes. Stars burn for ages. If lifelike processes at tiny scales occurred in femtoseconds or attoseconds, trillions of generations could pass during the blink of a human eye. By the time our detector records a single event, an entire history might have unfolded and vanished. Or the opposite could be true. Some hidden sector process could evolve so slowly that the age of the universe is only its morning. Either way, mismatch in timescale can make intelligence, adaptation, or persistence look like randomness. But can randomness hide order? Yes, sometimes. The motion of molecules in a gas looks random, but from that randomness emerge pressure, temperature, and sound. The activity of neurons is messy, but from it emerges thought. The genetic mutations that drive evolution are partly random, but selection gives them direction over time. A single ant may seem simple, but a colony solves complex problems. Pattern does not always live where we first look. It can emerge statistically, collectively, indirectly. If a subatomic lifelike system existed, perhaps no single particle would be alive, just as no single carbon atom in your body is alive. Life could be a relationship among many events. This is important because people often imagine subatomic life as tiny creatures sitting on electrons, as if shrinking a human into a nucleus could make sense. It does not. The inside of an atom is not a miniature room. There are no tiny floors, tiny skies, or tiny furniture. The rules there are not scaled-down versions of our world. At very small scales, quantum fields dominate. Particles are excitations, interactions are probabilistic, and position itself has limits of meaning. So realistic speculation must avoid cartoon thinking. If life exists at subatomic levels, it would not look like life. It would not have organs. It might not have location in the way we understand location. It would be a process in physics. The closest analogies may come from self-organizing systems. A whirlpool is not made of special water. It is a pattern in flowing water. A flame is not a substance. It is a chemical reaction maintaining a shape, while fuel and oxygen flow through it. A living cell is a pattern made of atoms that are constantly replaced. Much of your body's matter changes over time, yet you remain you because the organization persists. In that sense, life is like a song played on changing instruments. The notes matter more than the individual atoms. So if physics can support persistent songs at smaller scales, perhaps the smallest aliens would not be things, but songs in fields. Fields are not optional background decorations in modern physics. According to quantum field theory, every type of particle corresponds to a field spread through space-time. The electron field, photon field, quark fields, gluon fields, Higgs field, and others are fundamental parts of our best description of nature. Particles appear as quantized excitations of these fields. This means that what we call an electron is not a tiny bead independent from the universe, but a ripple in a field with very precise properties. If lifelike organization existed at this level, it might be less like a creature made of particles and more like a stable, self-modifying choreography among fields. Could fields support complex structures? In known physics, yes, fields can form patterns. Electromagnetic fields form waves. Quantum fields produce particles. In condensed matter systems, collective excitations can behave like quasi-particles. Superconductors, superfluids, plasmas, and magnetic materials reveal that many particle systems can create emergent behavior not obvious from individual components. Topological defects can appear in fields, like stable knots or twists in an order parameter. Cosmic strings and other topological relics have been proposed in some early universe theories, though not confirmed. The universe already shows that fields can hold structure. The question is whether any such structures can become lifelike. One of the most fascinating places to think about unusual organization is plasma. Plasma is often called the fourth state of matter, a gas so energized that electrons are separated from nuclei, forming a soup of charged particles influenced by electromagnetic fields. Stars are plasma, lightning is plasma, the solar wind is plasma, nebulae glow because of plasma processes. Plasma can form filaments, double layers, waves, instabilities, and self-organized structures. Some speculative discussions have wondered whether complex plasma systems could show lifelike behaviors under certain conditions. This does not mean plasma is alive, but it reminds us that matter can organize in surprising ways outside biology. A star, for example, is not alive. It does not reproduce with inherited variation in the biological sense. It does not store genetic information or adapt through Darwinian evolution. Yet a star is a long-lived, self-regulating object where gravity pulls inward and fusion pressure pushes outward. It processes energy, it changes over time, it creates elements, it shapes planets and chemistry. It is not life, but it is a cosmic engine of order. If life is defined too loosely, everything dynamic becomes alive and the word loses meaning. If it is defined too narrowly, we may miss unfamiliar forms. The challenge is to keep the mystery without dissolving the science. Now consider environments more extreme than Earth. Inside neutron stars, matter may be compressed into states we cannot reproduce fully in laboratories. Neutron stars are the collapse cores of massive stars, objects so dense that a teaspoon of their material would have an enormous mass. Their interiors may contain superfluid neutrons, superconducting protons, exotic nuclear phases, perhaps even deconfined quark matter depending on conditions. Their magnetic fields can be trillions of times stronger than Earth's. Their crusts may contain nuclear pasta, strange phases of matter arranged under crushing pressure. Could such an environment host complex information patterns? We do not know, but it is a reminder that matter has forms far beyond ordinary chemistry. A living organism inside a neutron star in the biological sense is not realistic. Normal atoms cannot survive there. Molecules as we know them cannot exist under such pressure. But lifelike processes do not have to be chemistry if the definition is abstract. Could stable patterns in superfluid vortices, magnetic fields, nuclear arrangements, or quark matter store information and evolve? That is highly speculative, and there is no evidence. Yet if such patterns existed, humans would almost certainly not recognize them from Earth. We cannot visit a neutron star. We cannot scoop its interior into a microscope. We infer its secrets through radiation, gravitational waves, mass, radius, spin, and theory. A living pattern there would be buried under physics so extreme that even non-living matter remains mysterious. The same is true near black holes. Black holes are not cosmic vacuum cleaners in the simple cartoon sense, but regions where gravity curves space-time so strongly that inside the event horizon, escape becomes impossible. Around black holes, matter can form accretion disks heated to extreme temperatures. Magnetic fields twist. Jets launch across thousands of light years. Particle acceleration becomes violent. Near the event horizon, time and energy behave in ways that challenge intuition. Could subatomic or field-like patterns exist there? Almost certainly complex physics exist there. Life, as we know it, could not. But if there are alien forms based on fields, plasma, or exotic matter, the universe's most extreme laboratories might be places where our definitions fail first. There is also the dark matter question. Most matter in the universe appears not to be the ordinary atomic matter that makes stars, planets, and people. Observations of galaxy rotation, gravitational lensing, cosmic structure, and the cosmic microwave background strongly support the existence of dark matter, though its particle nature remains unknown. Dark matter interacts gravitationally, and, as far as we know, very weakly or not at all through electromagnetic forces. That means it does not shine, absorb light, or form ordinary atoms. If dark matter is made of one simple particle with little self-interaction, it may not form complex structures like chemistry. But if the dark sector has its own forces, particles, or interactions, complexity becomes more conceivable. This is one of the strangest scientifically cautious possibilities. Maybe there is a hidden world not because it is far away, but because it is nearly invisible to electromagnetic light. If dark matter has dark electromagnetism, dark atoms, or hidden interactions, then in principle it could form structures that ordinary matter barely notices. This remains speculative. Many models exist and evidence is limited. But the idea is not simply fantasy. Physicists seriously explore dark sectors because the standard model does not explain everything. Could dark matter, life exist? We have no evidence. Could hidden sector complexity exist? It is not ruled out in all forms, and if it did, we might be like ghosts passing through another universe without touching it. Imagine two civilizations occupying the same galaxy, one made of ordinary matter and one made of hidden sector matter. They might pass through each other without fire, collision, or recognition. Their stars, if they had dark radiation, would be invisible to our eyes. Their chemistry, if it existed, would not use our photons. Their bodies, if bodies are even the right word, would not cast shadows in our light. We might detect them only through gravity or tiny deviations in experiments. To them, our world might be equally ghost-like. The Milky Way could be layered with realities that share gravity but not touch, and every night sky could be missing half its architecture. But here the discipline of science must speak clearly. There is no confirmed dark matter life. There is no evidence of hidden alien civilizations made of dark atoms. Most dark matter may be too simple, too diffuse, or too weakly interacting to support lifelike complexity. To form life, matter usually needs rich interactions, stable structures, energy gradients, and information storage. Ordinary matter has electromagnetism, which allows atoms, chemistry, light, and complex bonds. If dark matter lacks similar forces, it cannot easily build complexity. The idea is fascinating because it shows a loophole in our search, not because it proves aliens are already around us. Another candidate often mentioned in hidden cosmic stories is the neutrino. Neutrinos are tiny, electrically neutral particles that interact through the weak nuclear force and gravity. They are produced in nuclear reactions, supernova, radioactive decay, and the early universe. Trillions of neutrinos pass through your body every second, mostly without interacting. They can pass through Earth as if it were almost transparent. Neutrinos have mass, but extremely small mass compared with charged particles. They oscillate between types, revealing deep physics beyond the simplest early models. But could neutrinos form life? As far as known physics suggests, neutrinos interact too weakly to easily build stable complex structures. They are ghostly, not social. Still, neutrinos teach a lesson. Something can be everywhere and remain nearly invisible. For most of human history, neutrinos were completely unknown. They passed through kings, deserts, oceans, temples, storms, and bones without leaving a story. Only in the 20th century did physics infer and then detect them. They were not mythical, they were real, but hidden by weak interaction. This should humble us. If one class of particles could be so abundant and so difficult to catch, perhaps other hidden layers of nature exist beyond our current senses. Not life necessarily, but hidden reality. And where hidden reality has structure, imagination begins to ask whether hidden life is possible. One of the deepest obstacles is communication. We often think alien life must announce itself. It must send signals, build megastructures, alter atmospheres, or leave artifacts. But most life on Earth did none of that for most of Earth's history. For billions of years, Earth was a microbial planet. No radio signals, no cities, no telescopes, no spacecraft. yet it was alive. Even today, most life is microbial, silent, and indifferent to cosmic communication. If life exists at subatomic scales, why would it communicate in ways we understand? It might not know we exist. It might not have intelligence. It might not have motives. It might not even have a boundary between self and environment like we do. This brings us to a second twist. Maybe intelligence is not the best thing to search for. Maybe life is far more common than intelligence, and unfamiliar life may be common in forms that never become technological. On Earth, intelligence capable of radio astronomy appeared very late. Bacteria did not need rockets to be successful. They colonized every environment they could reach. They transformed the atmosphere. They survived catastrophes. They are still here. If alien life exists at tiny scales, it may not be building subatomic cities. It may simply persist, adapt, and flow through physical niches. We might miss it because we are looking for ambition, while the universe mostly produces survival. But could there be something like evolution at subatomic levels? Evolution requires variation, inheritance, and selection. In chemistry, molecules can vary. Some forms copy better than others. Environments favor certain structures. In biology, genes transmit variations across generations. At subatomic scales, inheritance is hard to imagine because particles of the same type are identical in known physics. One electron is not born with a little scar or personality that it passes to another electron. Electrons are fundamentally indistinguishable. This is a major problem for simple particle life ideas, but systems of many particles can have states, arrangements, correlations, and histories. Evolution would have to act on configurations, not individual particles. For example, in condensed matter physics, the same electrons can collectively produce different phases: metal, insulator, superconductor, magnet. The identity of the particles does not change, but the organization does. Information can live in arrangements. A magnetic domain can point one way or another. A defect in a crystal can move and interact. A vortex in a superfluid can carry quantized circulation. A pattern can be copied if a process creates similar patterns. If selection-like dynamics exist, some patterns may persist better than others. This is not biology, but it shows how matter can have memory and behavior beyond individual particles. Lifelike evolution at subatomic scales would likely require collective states. The word subatomic itself can mislead us. Below atoms, there are not simply smaller pieces behaving like mechanical gears. There are scales, nuclei, nucleons, quarks, leptons, gauge bosons, fields, and perhaps unknown layers. A nucleus can have structure. Nuclear reactions can transform elements. Quark gluon plasma existed in the early universe and can be briefly created in particle colliders. But these conditions are extreme and short-lived. Most subatomic events do not form gentle environments. They are either too simple, too violent, or too fleeting. That is why ordinary life appears at the molecular scale. Molecules offer a sweet spot between stability and flexibility. They are complex enough to store information and reactive enough to change. This sweet spot may be one reason Earth life is chemical rather than subatomic. Chemistry gives life a library of shapes. Carbon forms chains, rings, branches, double bonds, aromatic systems and polymers. Water dissolves and transports molecules. Hydrogen bonds allow DNA base pairing and protein folding. Membranes separate inside from outside. Enzymes speed reactions without being consumed. The temperature range of liquid water is forgiving enough for complex chemistry. Compared to this, subatomic particles offer fewer stable building blocks under ordinary conditions. So if alien life exists below atoms, it may require environments very different from Earth, perhaps places where exotic collective behavior becomes rich enough to replace chemistry. Now listen carefully to the silence between atoms. Most of an atom's volume is not filled with solid material. The nucleus is tiny compared with the electron cloud. Yet matter feels solid because electrons resist being pushed into the same quantum states and because electromagnetic forces push charged particles apart. You never truly touch a table in the simple sense. The electrons in your hand and the electrons in the table repel, while quantum rules maintain structure. Reality is already stranger than fiction. The solid world is a force pattern. Your body is not a block of stuff. It is a stable storm of fields, particles, and energy flows. Life at our scale is already an emergent illusion built from invisible rules. That does not make life less real. A rainbow is not a physical object you can hold. but it is real as an optical phenomenon. A wave in the ocean is not a permanent piece of water, but it is real as a pattern of motion. You are real not because your atoms are permanent, but because your organization persists long enough to remember yesterday and imagine tomorrow. This understanding opens a door. If life is a pattern, then the material substrate matters. But it may not be the whole story. Carbon chemistry is one substrate. Could plasma be another? Could quantum fields be another? Could hidden sector matter be another? The answer is unknown, but the question is scientifically meaningful when framed with caution. A powerful concept here is emergence. Emergence happens when many simple parts create behavior that is not obvious from each part alone. No single water molecule is wet, but many water molecules together create wetness. No single neuron understands language, but networks of neurons can produce speech, memory, and imagination. No single ant designs a colony, but colonies can build, farm, defend, and explore. Life itself may be an emergent state of chemistry under the right conditions. If so, perhaps alien life could emerge wherever the right kind of complexity, energy flow, and memory occur, even if the underlying parts are not biological molecules. But emergence has limits. Not every complex system is alive. Clouds form patterns, but they do not evolve lineages. Galaxies spiral beautifully, but they do not metabolize in a biological sense. Crystals grow, but their copying lacks open-ended evolution in the same rich way as genomes. A hurricane maintains itself by feeding on warm ocean water, but it has no hereditary memory. For subatomic life to be more than poetic metaphor, it would need something like open-ended complexity. It would need the capacity to generate novelty, preserve some of it, and be shaped by conditions. Without that, we are only renaming physics as life. This is where the idea becomes more refined. We do not ask, are particles alive? We ask, can there exist a physical system below ordinary chemistry with heredity, energy flow, boundary-like organization, and adaptive persistence? If yes, then it may be life by a broad scientific definition. If no, then subatomic life remains only a metaphor. At present, we do not know any confirmed system like that. But we also do not know all possible physical systems in the universe. We have not explored every environment, every hidden sector, every extreme state of matter, or every kind of self-organizing field. The honest answer is not belief. The honest answer is uncertainty with constraints. Now imagine a detector deep underground, waiting for rare particles. It is shielded from cosmic rays by rock. It watches for tiny flashes of light, tiny bursts of energy, tiny interactions. Scientists analyze the data with exquisite care. Most events are background, some are noise, some are known particles. A rare signal might hint at dark matter or neutrinos, but what would life look like in such data? If a hidden life form interacted once every billion passages, would we see biology or scattering? If its internal processes used particles that do not couple to electromagnetism, would our sensors register anything at all? Perhaps we could be surrounded by hidden complexity and only detect occasional meaningless fingerprints. This sounds almost mystical, but it is actually a lesson in measurement. Measurement is not passive seeing, it is interaction. To observe something physically, it must affect your instrument. Light must scatter from it, or it must deposit energy, pull gravitationally, alter a field, trigger a chemical reaction, or change a quantum state. If something does not interact with you in accessible ways, it is effectively invisible. This is why dark matter is dark. This is why neutrinos are hard to detect. This is why gravitational waves required astonishingly sensitive instruments. Reality can be present without being obvious. The universe does not owe our senses a complete report. The history of science is full of hidden things becoming visible only when concepts and instruments matured. Microbes existed before microscopes. Infrared radiation existed before detectors. X-rays passed through bodies before we knew how to image bones. Radio waves crossed the sky before antennas translated them. DNA carried heredity before its structure was known. The cosmic microwave background filled space before radio astronomy recognized it as ancient light. Gravitational waves stretched space-time before interferometers became sensitive enough to detect them. Each discovery expanded reality, not because reality changed, but because our questions did. Maybe life too has hidden categories waiting for the right question. Still, there is danger in this thought. Humans love to fill the unknown with creatures. We see faces in clouds, intentions in storms, messages in randomness. Scientific humility requires restraint. We cannot claim subatomic alien life just because it is interesting. We cannot turn every unexplained signal into an organism. We cannot use mystery as evidence. The correct scientific position is that subatomic life is not known to exist, and many forms of it may be physically unlikely. But the concept forces us to examine our assumptions. It asks whether our search for life is too tied to human scale, human chemistry, human time, and human senses. A major challenge is the boundary of the self. Every known living cell has some kind of boundary. A membrane separates inside from outside, allowing the organism to control chemistry, maintain gradients, and protect information. Without boundaries, metabolism dissolves into environment. But at subatomic levels, what counts as a boundary? A field configuration might have a topological boundary. A plasma structure might have electromagnetic confinement. A droplet of exotic matter might have surface tension or pressure balance. A dark sector object might be bound by hidden forces. Or maybe subatomic lifelike systems would be distributed, not enclosed, more like a network than a cell. But without some distinction between self and not self, life becomes difficult to define. Another challenge is replication. Biological replication is not perfect, and that imperfection matters. DNA copies with high accuracy but occasional mutation. Cells divide, populations vary, natural selection operates. A subatomic system would need a way to produce similar patterns with variation. Perhaps field patterns could split. Perhaps plasma structures could seed new structures. Perhaps hidden sector chemistry, if it exists, could replicate. Perhaps quantum error-correcting-like structures could preserve and propagate information. These are speculative analogies. But they show the kind of mechanism required. A particle simply existing is not enough. A pattern must make descendants. Then comes adaptation. Life does not just repeat, it responds across generations. Bacteria evolve antibiotic resistance. Plants evolve pigments and defenses. Animals evolve senses and behaviors. The earliest life on Earth probably began as chemical systems capable of evolving, before true cells existed as we know them. If subatomic life exists, adaptation might look nothing like biology. It could be a shift in stable configurations under environmental pressure. It could be selection among field states. It could be energy pathways becoming more efficient. But if there is no inheritance and no selection, then there is no evolution, only dynamics. This brings us to perhaps the most profound twist of all. Maybe life is not a substance, but a threshold. Below a certain level of complexity, matter simply reacts. Above that threshold, matter begins to preserve information about how to keep reacting in useful ways. At higher thresholds, it evolves. Higher still, it senses. Higher still, it predicts. Higher still, it becomes conscious, maybe. In this view, life is not a category with sharp walls, but a phase transition in organization. Just as water becomes ice under certain conditions, chemistry may become biology under certain conditions. Perhaps other substrates can cross similar thresholds. The subatomic question asks whether such a threshold can exist below chemistry. What would the universe look like if life is a general tendency of matter under the right conditions? Not inevitable, not magical, but possible wherever energy flows through complex systems capable of memory. Then planets with water are not the only stage. Icy moons, hydrothermal vents, atmospheric hazes, methane lakes, plasma clouds, hidden sectors, and exotic interiors all become parts of a larger map. Most may be sterile. Some may be pre-life. A few may cross the threshold, and some might be so unlike us that the word alien becomes too small. But let us not forget why the molecular scale is so powerful. Atoms are small enough to build complexity and large enough to be stable under many conditions. Molecules have shapes, charges, bonds, rotations, vibrations, and interactions. They can form networks. They can catalyze reactions. They can store sequences. This is why carbon-based life is not arbitrary. It is deeply supported by chemistry. Silicon is sometimes imagined as an alternative, but silicon chemistry in Earth-like conditions is generally less versatile for life than carbon. Ammonia, methane, or other solvents might support exotic chemistry under certain conditions, but they still operate at molecular scales. Subatomic life would need an equally rich toolkit, and known particle physics does not obviously provide one in ordinary environments. So why take the idea seriously enough to discuss for an entire journey? Because the limits of known life are not the limits of possible organization. Because we have only one example of biology. Because the universe is far larger, older, colder, hotter, denser, emptier, and stranger than Earth. Because matter can exist as plasma, degenerate matter, superfluid, superconducting phases, quark-gluon plasma, Bose-Einstein condensates, and perhaps unknown states. Because dark matter dominates mass yet remains mysterious. Because information may be as fundamental to life as carbon. And because the history of science teaches us that the obvious universe is rarely the whole universe. Now close your eyes for a moment and imagine shrinking down into your own hand. Skin becomes a landscape, cells become cities, molecules become machines, proteins twist and fold like living sculptures. DNA coils like a library written in chemistry. Go smaller. Atoms become open spaces ruled by probability. Electron clouds blur into mathematical shapes. Nuclei sit like dense suns. Go smaller still. Protons reveal quarks bound by gluons, a storm of strong force so intense that trying to isolate a quark only creates more particles. Go deeper, and particles become field excitations. The solidity of the body dissolves into rules. Somewhere in that descent, the familiar word life loses its grip. But maybe something else gains meaning. At our scale, we see cells. At another scale, perhaps the cell is not the basic unit. Perhaps a living system could be a stable loop of interactions, a self-protecting knot in a field, an evolving pattern in a hidden plasma, a chain of transitions inside exotic matter. It would not be alive by Earth's recipe. It might not eat, breathe, age, sleep, or die like us. It might not have a face. It might not have a place where one could point and say, "There it is." It might be distributed across probabilities, or embedded in correlations, or carried by excitations that exist only under extreme conditions. One reason we might never know is that our own existence filters reality. We evolved to notice things relevant to survival on Earth: food, predators, faces, weather, movement, day and night, warmth and cold. Our instruments extend those senses, but our concepts still guide what we build. We built telescopes because stars shine. We built microscopes because cells scatter light. We built radio receivers because electromagnetic waves can carry signals. We built particle detectors because theories predicted particles. But if life does not shine, does not scatter, does not grow in a dish, does not use DNA, and does not produce chemical waste, it may not enter our search image at all. A search image is powerful. A bird hunting insects notices insect-like movement. A doctor trained on familiar diseases recognizes familiar symptoms. A SETI researcher looks for signals that technology might produce. An astrobiologist looks for biosignatures shaped by chemistry. But the alien can be missed when it does not match the image. On Earth, life surprised us in boiling vents, acidic pools, radioactive waste, deep rocks, frozen deserts, and high atmosphere. These extremophils are still biochemical life, but they widened our imagination. They taught us that life is more flexible than we once believed. Subatomic life would require an even greater widening, perhaps beyond anything biology currently permits. There is an important difference between unknown life and unknowable life. Unknown life is something we have not found yet, but could detect if we looked properly. Unknowable life would be forever beyond interaction, making it scientifically unreachable. Science deals best with the first. If subatomic or hidden sector life interacts with our world in any measurable way, then in principle we might someday detect patterns. If it never interacts except through gravity in a completely indistinguishable way, it may remain beyond confirmation. A hypothesis that can never be tested becomes philosophy, not science. The best version of this idea asks what measurable signs could reveal unfamiliar lifelike organization. What signs might those be? Not a tiny heartbeat, not a microscopic face, not a message in English hidden in particle collisions. More likely, scientists would look for anomalous patterns that cannot be explained by known physics, then test whether those patterns show information processing, self-maintenance, adaptation, or non-random organization. For example, unusual correlations in particle events, unexpected energy distributions, repeated structure in plasma systems, strange stability and field configurations, or hidden sector interactions could lead to new physics. Only much later, if those systems showed lifelike properties, could anyone responsibly use the word life. The path would begin not with aliens, but with anomalies, and anomalies are difficult. Most anomalies disappear. They become instrument errors, statistical fluctuations, background contamination, calibration issues, or incomplete models. Science is patient because reality is subtle and humans are fallible. A real discovery must survive skepticism. That is why no one should claim subatomic life based on mystery alone. The universe contains enough known strangeness without inventing false certainty. Neutrino oscillations were real because experiments confirmed them. The Higgs boson was real because data reached extraordinary significance in the expected channels. Gravitational waves were real because signals matched general relativity across detectors. Alien life, especially of a radical kind, would require evidence just as strong. Still, even without evidence, the idea reshapes our view of ourselves. We are not rulers of scale. We are middle creatures, living between the very small and the very large. Above us are planets, stars, nebulae, galaxies, clusters, filaments, and the observable universe. Below us are organs, cells, proteins, atoms, nuclei, quarks, fields, and perhaps deeper layers not yet known. We exist in a narrow band where chemistry is stable, temperatures are gentle, and time flows at a rhythm our brains can follow. We call this normal because we were born here. But from the universe's perspective, our normal may be one tiny province. There may be forms of complexity too large for us to recognize as life. A biosphere is alive, but is Earth as a whole alive? Not as an organism in the strict sense, but it has feedback systems. A galaxy is not alive, but could there be lifelike processes at galactic scales over billions of years? Speculative, yes. Similarly, there may be forms too small. The fact that both extremes challenge us suggests that life may be scale-dependent in recognition. We identify life most easily near our own scale. Too small becomes chemistry. Too large becomes environment. But perhaps life can hide by pretending to be background. Imagine a civilization made of molecular life, trying to detect a civilization made of slow geological processes. It might miss it. Imagine a creature whose thoughts take 10 million years. We would call it a mountain range. Imagine a being whose thoughts take a trillionth of a second. We would call it noise. The word intelligence depends on tempo. The word organism depends on boundary. The word communication depends on shared channels. Without overlap, two forms of existence can pass through the same reality without meeting. Now we must ask the most delicate question. Could consciousness exist at subatomic scales? Here, caution is essential. There is no scientific evidence that isolated particles are conscious. There is no evidence that electrons think, that quantum fields feel, or that consciousness is automatically present wherever quantum mechanics appears. Human consciousness, as far as neuroscience can investigate, depends on complex biological brains, information integration, memory, attention, and dynamic neural activity. Quantum mechanics underlies the matter in brains, but that does not mean consciousness is a simple quantum effect. Claims that consciousness is explained by vague quantum mystery are usually not grounded. However, the broader question of whether consciousness could arise in a non-biological substrate remains open in philosophy and cognitive science. Artificial intelligence raises one version of this. Alien biology raises another. If consciousness depends on information processing in the right architecture, then maybe it is substrate independent to some degree. But subatomic consciousness would require extraordinary complexity and stability. A single particle cannot plausibly host a mind. A simple quantum state is not a thought. If there were conscious subatomic life, it would likely be a vast collective process relative to its own scale, not a tiny soul attached to matter. This remains far beyond evidence. The safer and more scientific idea is not subatomic consciousness, but subatomic lifelike organization. Consciousness is a high bar. Life is already hard. Intelligence is harder. Technology is harder still. We should not jump from maybe hidden complexity to invisible particle people. The universe may host many levels of organization without awareness. Most Earth life is not conscious in the human sense. Bacteria are alive but not reflective minds. Plants sense and respond but do not think like animals. A subatomic system, if it existed, might be more like a microbial ecology than a civilization. That is still astonishing enough. Now let us return to the early universe. In the first moments after the Big Bang, the cosmos was hot, dense, and radically different from today. Particles and radiation filled space. As the universe expanded and cooled, forces separated, particles formed, nuclei emerged, atoms later combined, stars ignited, and heavier elements were forged. The early universe may have passed through phase transitions, leaving behind relics or defects depending on the physics involved. If exotic stable structures formed, then some might still exist. Again, there is no evidence that such relics are alive. But the early universe reminds us that ordinary matter is only one chapter in a long physical story. Could life have begun before planets? Conventional life likely needed heavy elements, chemistry, and environments like planets or moons. The first stars had to create carbon, oxygen, nitrogen, phosphorus, sulfur, iron, and other elements used by biology. But if life is abstracted beyond chemistry, one might ask whether pre-chemical lifelike patterns could exist in earlier epochs. The problem is harsh. The early universe was hot, dense, and rapidly changing. Stable complex structures were difficult. Still, hidden sectors or field defects, if they existed, could have had their own histories. This is speculative cosmology, not established biology, but it stretches the timeline of possibility. Another possible hiding place is not far away at all. Ordinary matter. Could subatomic life exist inside rocks, bodies, oceans, or air? With known physics, this seems unlikely if we mean independent life below atoms. The interior of ordinary matter is dominated by electromagnetic chemistry and nuclear stability. Subatomic particles are bound into atoms and nuclei. They do not freely assemble into complex evolving systems beneath chemistry under normal conditions. But if hidden sector particles pass through ordinary matter, they could occupy the same space without participating in our chemistry. In that sense, hidden life, if it existed, might overlap with us spatially while remaining separate physically. This overlap idea is haunting. You are sitting inside invisible flows already. Neutrinos pass through you. Cosmic rays strike the atmosphere above you. Dark matter, if it consists of particles passing through Earth, may be streaming through your body right now. Radio waves, magnetic fields, thermal photons, gravitational fields, and quantum fluctuations surround you. Most of this is not alive, but it proves that human-scale matter is not a sealed container. We are porous to the universe. The body is not an isolated island. It is a temporary pattern in a cosmic ocean of fields and particles. If hidden life existed, proximity would not guarantee awareness. There is a beautiful humility in this. Humans often imagine first contact as a meeting between faces. A spacecraft lands, a signal arrives, a message is decoded. But first contact with truly alien life might be stranger. It might begin as a mathematical anomaly in a detector, a repeated pattern in noise, a discrepancy in cosmology, a signal that looks meaningless for decades until a new theory reveals structure. We may not shake hands, we may not hear voices, we may discover that life is a deeper category only after rewriting physics. And even then, the life we find may never know we found it. Another twist appears when we consider that we ourselves are subatomic from another perspective. To a galaxy, humans are almost unimaginably small. Our cities are thin chemical films on a rocky planet orbiting an ordinary star. Our entire history is a flicker. If a galaxy-scale observer existed, it might not notice us individually. It might detect Earth only as a spectral anomaly: oxygen, methane, water vapor, industrial gases, nighttime lights. It would infer life from indirect signatures. That is exactly how we may have to detect life at scales unlike ours, not by seeing organisms, but by noticing that matter behaves as if information is maintaining itself. This is why biosignatures are such a profound concept. A biosignature is not life itself. It is a clue life may be present. Oxygen in an atmosphere can be produced by life, but also by non-living processes under some conditions. Methane can be biological or geological. Organic molecules can form without life. A true detection requires context. The same would be true for subatomic life. An unusual pattern would not automatically mean life. It would require ruling out known physics and then showing lifelike properties. The more alien the life, the harder the proof. the proof problem may be so hard that subatomic life, even if real, could remain forever debated. Imagine a pattern in dark matter halos that some scientists interpret as hidden sector biology, while others explain it as new non-living physics. Without samples, controlled experiments, or direct interaction, consensus could take centuries. This is not unusual. Science often advances through long arguments. But the more extraordinary the claim, the more extraordinary the evidence must be. Subatomic alien life would be among the most extraordinary claims ever made. It would transform physics, biology, philosophy, and our place in the cosmos. Let us now explore a more grounded analogy: viruses. Viruses are not cells. They do not metabolize independently. They cannot reproduce without hosts. Some scientists consider them at the edge of life rather than fully alive. Yet they carry genetic information, evolve, and shape ecosystems. They show that life is not always a self-contained organism. A virus is a biological program that becomes active in the right environment. If something subatomic were lifelike, maybe it too would be context-dependent. It might not be alive alone, but only as part of a larger physical process. Life may sometimes be relational, not isolated. Another analogy is prions. A prion is a misfolded protein that can induce other proteins to misfold. It has no DNA, no RNA, no metabolism, no intention. Yet it propagates structure. It is not alive in the usual sense, but it shows how information can copy through shape alone. Crystals also copy structure when they grow. Fire spreads chemical reactions. These edge cases remind us that replication and propagation can occur without full life. Subatomic systems might have prion-like or crystal-like propagation of states, but to become life, they would need richer variation and selection. Then there are autocatalytic chemical networks, where molecules help produce each other, creating self-sustaining cycles. Some origin of life research explores how such networks might have preceded genetic life. Before DNA, there may have been RNA-like molecules, metabolic cycles, lipid compartments, or mineral surface chemistry. The origin of life on Earth is still unsolved, though many pieces are known. This matters because even at the chemical level, the transition from non-life to life is not a single magic spark. It is a gradual deepening of organization. If lifelike systems exist elsewhere, they too may occupy grey zones. Subatomic life, if possible, might exist in a grey zone so unfamiliar that we do not have words for it. It may be neither organism nor machine, neither chemistry nor simple physics. It may be a pattern that evolves but does not metabolize in a recognizable way. It may store information but not in sequences. It may have boundaries but not membranes. It may reproduce but not by division. It may die when its field configuration decays. It may feed on gradients we do not perceive. It may inhabit environments that would annihilate ordinary matter. This is why it would be alien in the deepest sense, not foreign biology, but foreign ontology. Ontology asks what kind of thing something is. A rock is an object. A wave is a process. A species is a lineage. A mind is an experience. A society is a network. A field is a physical entity spread through space. Life may not belong to one category. Earth organisms are objects, processes, lineages, networks, and information systems all at once. Subatomic life could emphasize different aspects. It might be less object-like and more process-like. If our minds insist on object-shaped aliens, we may miss process-shaped life. The phrase, "we'd never know," sounds dramatic, but it has several meanings. We might never know because the life does not exist. We might never know because it exists but leaves no measurable trace. We might never know because it leaves traces we misinterpret. We might never know because its timescale is incompatible with ours. We might never know because its substrate interacts through forces we have not discovered. Or we might know someday, but only after science becomes so advanced that our current categories seem primitive. Never may mean never for us. Not never for intelligence in the far future. Future instruments may change everything. Quantum sensors are becoming more sensitive. Gravitational wave astronomy has opened a new way to observe the universe. Neutrino observatories continue to improve. Dark matter experiments probe rare interactions. Particle colliders test high-energy physics. Atomic clocks can detect tiny changes in time and fields. Astrophysical surveys map cosmic structure with increasing precision. If hidden complexity exists, it may first appear as physics, not biology. The path to the smallest aliens may pass through better measurement of the smallest forces, but even perfect instruments would need better theory. Data without concepts can be invisible. Before germ theory, microbes were not understood as disease agents. Before plate tectonics, continents were not understood as moving plates. Before quantum mechanics, atomic spectra were mysterious lines. Before evolution, biological diversity lacked its unifying mechanism. If subatomic life is possible, recognizing it might require a theory that unites thermodynamics, information, complexity, and fundamental physics in a new way. We may need a general theory of life that does not assume cells, DNA, or chemistry, but still remains testable. Scientists have already tried to think broadly about life. Some definitions emphasize Darwinian evolution. NASA has often used a working definition. Life is a self-sustaining chemical system capable of Darwinian evolution. This definition is practical for astrobiology, but it includes chemical, which may exclude stranger possibilities by design. Other approaches define life through autopoiesis, metabolism, information, free energy minimization, adaptive complexity, or organizational closure. No definition is universally accepted. This disagreement is not weakness. It reflects the depth of the problem. Life is easy to recognize in familiar forms and hard to define at the edges. A subatomic life hypothesis would demand an even more abstract definition. It might say life is a bounded, self-maintaining, information-bearing system that uses energy flows to preserve and reproduce adaptive organization. But each word becomes difficult. Bounded how? Information in what form? Energy flow from what source? Reproduction by what mechanism? Adaptive under what selection? This is why the idea is exciting and dangerous. It can become meaningful only when tied to mechanisms. Without mechanisms, it becomes poetry. With mechanisms, it becomes a research question. Let us walk through a possible imaginary, but physically respectful example. Suppose there is a hidden dark sector with two or more stable particles and a force similar to electromagnetism but invisible to us. Suppose these particles can form bound states, like dark atoms. Suppose dark radiation allows energy exchange. Suppose dense dark matter regions form cooling structures. In such a universe within the universe, complex dark chemistry might be possible. If there are stable compounds, energy gradients, and information-carrying structures, then some form of dark sector life is not logically impossible. But every suppose is a mountain. We do not know whether any of those conditions are real. Another example, suppose in extreme plasma environments, electromagnetic fields and charged particles create self-sustaining structures that can replicate under certain conditions. They would not be subatomic in the strict particle sense, because plasma structures can be larger than atoms, but their behavior is driven by charged particles and fields. If such structures showed heredity and evolution, they might be considered plasma life. Again, this is speculative. Known plasma phenomena are not life, but plasma reminds us that non-chemical systems can be complex, adaptive-looking, and difficult to classify. A third example, suppose topological defects in a field can store information in stable configurations. Topology can make certain structures robust because they cannot easily be unwound without crossing energy barriers. In condensed matter, topological states are real and important. In cosmology, topological defects are hypothetical in some models. If defects could interact, replicate, and evolve in a suitable environment, they might form a lifelike system. This is far beyond confirmed science, but it gives a shape to the question. Life might not require little particles arranged like beads. It might require stable differences protected by physical laws. The strange thing is that Earth life also uses protected differences. DNA stores information in sequences of bases. Proteins fold into shapes determined by chemistry. Cell membranes maintain inside-outside differences. Nervous systems encode differences into electrical and chemical states. Life is difference that resists erasure. Entropy tends to spread energy and erase gradients, but life locally maintains gradients by exporting disorder to the environment. A living thing is not a violation of entropy. It is a temporary island of order, powered by a larger flow toward disorder. This principle could, in theory, apply to non-chemical systems too. That is why thermodynamics may be the universal language of life. Any life form, no matter how alien, must deal with energy, entropy, and information. It must maintain organization in a universe where disorder tends to increase overall. It must use free energy. It must shed waste, even if waste means field disturbances or radiation rather than carbon dioxide. It must avoid equilibrium, because equilibrium is the death of organized process. A perfectly balanced system has no usable gradients. Life is a controlled imbalance. It is the art of not becoming still too soon. At the subatomic level, equilibrium and non-equilibrium physics are everywhere. Particle distributions, radiation fields, phase transitions, decays, scattering, and collective excitations all involve energy flow. The question is whether any of these flows can become organized in a self-sustaining, adaptive way. In ordinary particle collisions, events are too brief. In stable matter, chemistry dominates. In extreme astrophysical environments, complexity may exist, but observation is limited. In hidden sectors, interactions may be unknown. The door is not wide open, but it is not sealed by imagination alone. A deep meditative truth emerges here. We are asking whether the universe can dream in smaller languages than DNA. DNA is a language written in molecules. Neural activity is a language written in cells. Culture is a language written in minds. Technology is a language written in tools. But physics itself has languages: spin, charge, phase, topology, symmetry, energy, momentum, correlation. Perhaps somewhere, under conditions we have not recognized, those languages form sentences. Not sentences for us, not messages, but organized patterns with history. And if they exist, they might be the most ancient aliens of all. Would they know the stars? Maybe not. To a subatomic lifelike system, stars may be not points of light but background conditions. It might not have vision. It might not have space in the way we experience space. It might sense gradients, fields, collision rates, energy distributions, or boundary conditions. Its universe could be a landscape of potentials and probabilities. It might live inside a particle accelerator for a fraction of a second, inside a neutron star crust for 1,000,000 years, or inside a hidden dark cloud for the age of galaxies. Its sky might be mathematics. Would we be gods to it? Probably not. We might be irrelevant. Human beings like to imagine that smaller creatures experience us as giants, but bacteria do not worship us. They respond to chemistry. Dust mites do not comprehend architecture. Microbes in deep rock do not know the surface world. Scale does not create spiritual hierarchy. It creates disconnection. If subatomic life existed, we might pass through its world as slow-moving boundary conditions, massive rearrangements, or rare catastrophes. A footstep, a breath, a heartbeat, a particle collision in our tissues could be an apocalypse or nothing at all. Could we harm it unknowingly? This question is more philosophical than practical because we have no evidence such life exists. But it mirrors questions we already face. When we sterilize spacecraft, we worry about contaminating other worlds with Earth microbes. When we drill ecosystems, we disturb hidden biospheres. If hidden life existed in exotic substrates, our experiments might disturb it without awareness. Yet without evidence, we cannot build ethics around imaginary beings. The lesson is not fear. The lesson is humility. Discovery often expands moral imagination after it expands scientific knowledge. Now consider the opposite possibility. What if subatomic life exists but cannot affect anything large? Then it might never matter to us except philosophically. It would be a sealed poem inside physics. But if it can affect ordinary matter even slightly, then perhaps there are traces. Maybe not in laboratories yet, but in cosmic structure, stellar behavior, unexplained energy distributions, or rare events. Science would not call those traces life until proven, but someday a pattern might resist every non-living explanation. The first hint of the smallest aliens may not be a face at the window, but a curve on a graph. Human imagination often jumps to stories of hidden beings inside atoms, but the more realistic wonder is subtler. The universe may support categories of organization that do not map onto our senses. We already know this from mathematics. A phase transition can suddenly create order, a symmetry can break, a field can settle into a vacuum state. A chaotic system can produce attractors, a network can compute, a feedback loop can stabilize. None of these requires biology, but all are part of the broader grammar from which life may be built. The question is whether life is one chapter in that grammar or the title of the whole book. The answer may depend on how common origin of life processes are. If life on Earth began easily once conditions were right, then the universe may be full of biology. If it required an extremely rare sequence of events, life may be sparse. We do not know yet. Finding even microbial life on Mars, Europa, Enceladus, or an exoplanet would change the probability dramatically. If we find life with a separate origin, it would suggest life emerges readily. But if all life we find is chemical, carbon-based and water-dependent, that still would not exclude stranger life. It would simply show that familiar life may be the easiest to detect. Detection bias is everything. We detect what is loud in our instruments. Oxygen atmospheres are loud to telescopes. Radio signals are loud to antennas. Fossils are loud to geologists. Cells are loud to microscopes. But hidden life may be quiet. Microbes deep underground were once quiet to human science. Life in Earth's deep biosphere, living in rocks and sediments, shows that even familiar biology can occupy places we ignored. If Earth still hides biological surprises, how much more could the universe hide at scales we barely understand? A poetic but grounded way to say it is this: the alien may not be absent, it may be illegible. Legibility depends on shared structure. We can read DNA because all Earth life shares related chemistry. We can read starlight because atoms have spectral lines governed by quantum mechanics. We can read gravitational waves because general relativity predicts space-time ripples. To read subatomic life, we would need to know its alphabet. Without that, it becomes background. And perhaps many realities are not invisible because they are faint, but because we lack the alphabet. This idea also changes the emotional meaning of loneliness. When people ask whether we're alone, they often mean whether there are other minds among the stars. The silence of the sky can feel heavy. We send signals and hear no reply. We look for Earth-like planets and wonder if anyone looks back. But if life can exist in forms beyond our recognition, then the universe may be less lonely and more mysterious. The silence may not mean emptiness, it may mean translation failure. The cosmos may be whispering in modes we cannot yet hear, yet we must keep our feet on the ground. There is no confirmed alien life anywhere beyond Earth at this time. No microbial fossil from Mars has been universally accepted. No exoplanet biosignature has been confirmed as life. No radio signal has been proven extraterrestrial intelligence. No dark matter particle has been directly identified. No subatomic life has been detected. The honest wonder is not aliens are definitely inside particles. The honest wonder is, our current search may cover only a small part of what life could be. That distinction is the line between science documentary and misinformation. A realistic conclusion must balance awe and restraint. Life at the subatomic level faces enormous obstacles: lack of stable complex structures, difficulty of information storage, fragility of quantum states, weak interactions for many particles, absence of known replication mechanisms, and extreme detection challenges. These obstacles make many simple versions unlikely. But the universe contains unknown physics, hidden sectors, extreme matter, and emergent complexity. It may allow possibilities we have not modelled. The correct emotion is not certainty, it is disciplined astonishment. Now imagine a future scientist centuries from now studying data from a detector more sensitive than anything we have built. At first, the signal looks like noise, then it shows repetition, then variation, then adaptation to experimental conditions. The pattern resists known explanations. It appears to maintain information across interactions. It responds to energy gradients. It reproduces a structure in a hidden field. Decades pass, teams argue, new theories emerge. Slowly, the word life appears in papers, first cautiously, then more boldly. Humanity realizes that biology was not the only way matter learned to remember itself. That would be one of the greatest moments in history. Or imagine the opposite future. We search deeply and find no such life. We discover dark matter, map hidden physics, probe quantum fields, explore icy moons, study exoplanets, and conclude that life truly requires chemistry like ours. That too would be profound. It would mean the molecular scale is not just one possibility, but a rare cosmic doorway. It would make cells even more miraculous. Not in a supernatural sense, but in the sense of physical preciousness. Either outcome teaches humility. Either the universe is more alive than we imagined, or Earth life is more exceptional than we feared. The title asks why alien life might exist at the subatomic level and we'd never know. The answer is not because tiny aliens are hiding from us. It is because life, if defined broadly as adaptive information sustained by energy flow, may not always look biological. It is because our instruments are designed to measure physical properties, not living meaning. It is because scale can distort recognition. It is because some sectors of matter may interact weakly with ours. It is because time can move too fast or too slow for our perception. It is because the universe may contain forms of order that fall between our categories, not simple matter, not familiar life, but something in between. And maybe that is the deepest truth of this journey. The universe does not divide itself according to human vocabulary. It does not label one system alive and another not alive. It simply permits patterns, and some patterns endure. Some patterns consume energy. Some patterns copy themselves. Some patterns learn from selection. Some patterns become cells. Some cells become minds. Some minds look back into the quantum dark and ask whether the ladder continues below them. We are one such pattern, asking whether smaller patterns might also be searching, surviving, or simply existing beyond our recognition. So tonight, when you look at the night sky, remember that distance is not the only hiding place. The alien may be hidden by miles, by light years, by ice, by darkness, by time, by chemistry, by dimension, by interaction, or by scale. The most unreachable world may not orbit another star. It may exist in the rules beneath your fingertips. It may be written in fields, hidden in dark matter, flickering in plasma, or forbidden by physics entirely. We do not know. But the fact that we can ask the question reveals something extraordinary about us. We are matter that became curious about matter. We are atoms asking whether atoms are the final stage. We are the universe wondering how many ways it can become organized enough to wonder. And if subatomic alien life does not exist, the search still gives us a gift. It teaches us what life requires. It teaches us why cells are powerful. It teaches us why chemistry matters. It teaches us why information is sacred in the physical sense. Fragile, structured, and costly to maintain. It teaches us that life is not a simple label, but a deep process balanced between order and chaos. It teaches us that our bodies are not separate from physics, but expressions of it. Every heartbeat is quantum rules scaled into biology. Every thought is matter organized into meaning. Every breath is the universe briefly resisting silence. The final result is not a claim, but a widened horizon. Alien life might exist at the subatomic level if nature allows stable, energy-fed, information-bearing systems beneath ordinary chemistry, perhaps in hidden sectors, extreme states of matter, or field structures we do not yet understand. We might never know if such systems interact too weakly with us, operate on incompatible timescales, leave no recognizable biosignatures, or appear only as noise inside our instruments. But for now, no evidence proves they exist. The idea remains a scientifically inspired possibility at the edge of knowledge, a mirror held up to our assumptions about life. And perhaps that is enough for one night. Not every mystery must become certainty to change us. Some mysteries are doorways. They teach us to look again at the ordinary world, the table that feels solid but is mostly quantum structure, the body that feels continuous but is a flowing pattern, the stars that look silent but forge the atoms of life, the darkness that seems empty but may hold unseen fields. Somewhere between the smallest particle and the largest galaxy, life appeared at least once and opened its eyes. Whether it has opened them in other forms, at other scales, in other hidden layers of reality, remains one of the most haunting questions science can ask. So the next time someone says aliens must be out there, somewhere among the stars, remember the stranger possibility. They may not be out there in the way we expect. They may be beneath the idea of where. They may be too small to see, too fast to follow, too weakly interacting to touch, too different to name, or they may not exist at all. But the search for them forces us to define life more deeply than ever before. It forces us to see ourselves not as separate from the universe, but as one expression of its ability to organize matter into memory. In the end, the smallest alien may be impossible, or it may be the oldest neighbor we never knew. But until evidence arrives, the honest answer is wonder with discipline. The universe is not required to be simple. Life is not required to be familiar. and human knowledge is not finished. Somewhere beyond our instruments, or perhaps beneath them, reality may still be holding forms of order we have not learned how to recognize. If one day we discover that life can exist below atoms, then the universe will become more intimate and more terrifying at once, because the alien will no longer be only beyond the stars. It will be inside the silence of matter itself. End.